Okay, here is my resumed attempt to the section B of the speech paper 2. So question 1, we have a hybrid function like a cubic and combination of the exponential and linear function. It's talking about a scenic walking track from point O to point D, and it's shown below. All right. So the question says the minimum turning point of section OABC occurs at point A. And point B is a point of inflection, and the curve meets at the point C10. Distances are measured in kilometers. So firstly, we want to show that A equals to -1 and B equals to 0. We only have 1, 0 so far. So basically, we should try. Let f1 of x equals to -x, x plus a squared. f2 of x equals to e, x minus 1 minus x plus b, okay? Okay, so we have a common point. This is a discontinuous, this is a continuous point. So what I'm going to do is f1 of 1 equals to 0. So I actually show my substitution -1 times 1 plus a squared equals to 0. And that gives me a equals to -1, because this must be 0, okay? And f2 of 1 equals to 0. So I will be substituting the value in here, e to the power of 1 minus 1 minus 1 plus b equals to 0. So we know this bit will be 0, and therefore b equals to 0. And that's it. Before we proceed, we should actually use these two values. So I will be using my CAS calculator to do the demonstrations. Okay, here is my first problem. Define f1 of x is equal to -x times x minus 1 squared. Define f2 of x equals to exponential x minus 1 minus x plus 0. Okay, so now if I go to my graphs, I can see my f1 and f2 are already there. So we can actually put, for example, some domain constraint, say 0 to 1. Okay, that's one part. It's very small, so later on we will zoom in a little bit. And the other part is f2 from 1 to 2. Okay, we actually have 2 bits. And according to the diagram on the exam paper, I would say go back to Windows Zoom window settings from -0.6 to 2.6. X scale, let's use 0.2. Y minimum, -0.3. Y maximum is 1. And Y scale is 0.1. And that gives me a better understanding of these two curves, okay? All right, so the next thing I'm going to do is for the second part. If I've got 2 bits as 2 parts of the piecewise function, I will be differentiating them at the same time to do the second part. So I will try shift minus dx. And curly bracket, f1 of x, comma, f2 of x. All right, so we can get 2 expressions in one attempt. And let's go back and copy these 2 down, see how we go. F1 dash of x is equal to minus x minus 1, and then we have 3x minus 1. F2 dash of x is just ex minus 1 minus 1, if I'm not mistaken. Yep. If the two curves are meeting each other smoothly, that means differentiable at x equals to 1. So same gradient. This is what we want to show. So then I'm trying f dash 1 is equal to minus 1 minus 1, 3 minus 1. That gives me 0. F2 dash of 1 equals to e to the power 1 minus 1 minus 1. So that gives me, for example, 1 minus 1, 0. Same gradient at 1, 0. Therefore, they meet each other smoothly. All right, so let's have a look at the next part. We want to find the coordinates of point A, which is the minimum from 0 to 1. And also we want to find the coordinate of the point B, which is the point of inflection. And according to the diagram, that's also between 0 and 1. Both points are on y equals to f1 of x. So let's do this. So 1/3 minus 4 over 27, that's the local minimum, okay? And we can just do another second derivative to get the point of inflection on the cubic function part. Menu solve system of equations, 2 equations. Second derivative f1 of x equals to 0. Y equals to f1 of x. So we will have 2/3, comma, minus 2 over 27. And now let's go back and write this down. All right. The return track from point D to point O follows an elliptical path given by x equals to 2 cos t plus 2, y equals to e minus 2 sine t. And the parameter domain is half pi to pi, the t. So we want to find the Cartesian equation of this elliptical path. Firstly, we can recognize we can isolate cosine t and sine t. So x minus 2 divided by 2 equals to cosine of t. Y divided by bracket e minus 2 equals to sine t. And if we just, square everything, we can safely use cosine square t plus sine square t equals to 1. The Pythagorean identity will give us x minus 2 squared divided by 4 plus y squared divided by e minus 2 squared equals to 1. So that is a Cartesian equation. But bear in mind, we only have the return track from point D to point O. So it's like from here to here. Okay? So basically we just got a quarter ellipse. So the next part is to sketch the elliptical path from D to O on the diagram on page 10, which is on previous page. Before we sketch, we actually need to use the same viewing window on the CAS calculator. So let's have a look at the previous viewing window. Okay, so pretty much that's what we have now. We can add in some grids, menu 2, 6, 2. All right. We can also get a menu 2, 6, 3 lined grid. That looks better. But before we plot, we need to go to menu, graph entry, parametric. Okay. So now we can just type in the two equations. X equals to 2 cosine of t. And that's like plus 2. Yt is bracket e minus 1 times sine t. Oh, by the way, this is just my shortcut from computer. You can access the e from the pi button, okay? Actually, it's e minus 2. Don't forget to adjust your t domain, like pi over 2 to pi. And t step, I will say I'll use 0.03, using a smaller t step to show greater resolution on the curve, and then press enter. So basically, this is what we are expected to draw. And you can see it has a right-hand point here, joined together with the exponential function part. And also, this is, left-hand point. And to draw a nice ellipse, we must make sure the shape is pretty much like a quarter ellipse here, okay? So I would say this bit needs to be flat, and this bit needs to be, perpendicular, okay? Perpendicular gradient. You can actually trace a couple of points. Let's say menu, trace, graph trace. Trace. Pass plot or trace all. Anyway, let's just go back and sketch this one. So when you are sketching this one, make sure it's sufficiently it has certain curvature here, okay? It has certain curvature, like what I'm saying is flat here and perpendicular here. So use your pencil to have your best attempt. Okay. Finally, we want to write down a definite integral in terms of t that gives the length of the elliptical path from D to L, and find the length of the elliptical path from D to L. So this is a standard arc length question. So what we are applying is length equals to integral from smaller t value to a larger t value square root derivative of x squared. Well, derivative of x squared is, x is just minus 2 sine t, if I'm not mistaken, yep, squared, plus e minus 2 cosine of t, cosine squared. And we should write dt there. Never forget your infinitesimal. And then we find the length of the elliptical path from D to O. Give your answer in kilometers correct to 3 decimal places. Basically, we are integrating the speed function of this elliptical path. So what I'm trying to do on the CAS calculator will be as follows. Because we already have the parametric graph xy and y1 plotted, we can say, all right, we want to find a norm derivative t x1 of t, comma y1 of t. So basically, this is like some vector calculus skill. You find the velocity and then you take the norm, which is the speed. The length of the velocity is speed. So this is actually an equivalent expression to the square root expression for the integrand. Now we can just go for shift plus pi over 2, tab pi, answer t. Control enter. That gives me 2.25537 something. So correct to 3 decimal places. the answer should be 2.255 kilometers. And let's go back and complete the last one and move on to the next question. Okay, that is the first question. And I think it's not harmful to label the coordinates 0, 0. And at the beginning, if I substitute a half pi, I should be able to get a 2 here and e minus 2. So 2 here and e minus 2. Okay, righty-ho. Question 2. Let w equals to cease 2 pi over 7. So we want to verify that w is a root of z7 minus 1 equals to 0. So when z equals to w, left-hand side equals to w to the power of 7 minus 1 equals to cease 14 pi over 7, because that's basically 1 to the power of 7 cease 2 pi over 7 times 7, okay, using De Moivre theorem, minus 1. So it's equal to cease 2 pi minus 1. And cease 2 pi is 1 minus 1, that's 0, equals to right-hand side. Therefore, verified. Okay, the next thing is to list the other roots of z to the power of 7 minus 1 equals to 0 in polar form. So basically, this is saying z to the power of 7 equals to cease 2k pi. Because cease 2k pi is 1, and a k is going to be 0, plus or minus 1, plus or minus 2, and a plus or minus 3, etc. But we only need, for example, 7 distinct k values, because the maximum number of distinct solution is 7, okay? So if I just choose k equals to 0, I will have z equals to cease 0, which is cease 2 pi, etc. But it's equal to 1 anyway. I think it would be better to write this as cease 0, because the question wants polar form. And also, if I choose plus or minus 1, I should have cease plus or minus 2 pi over 7, which already included, one solution W from part A. And also we have cease plus or minus 2 lots of 2 pi over 7, 4 pi over 7, and as finally z equals to cease plus or minus 6 pi over 7. So totally there are 7 solutions. And on the Argand diagram below, plot and label the points that represent all the roots. So we know here we've got cease 0 equals to 1, and 7 equal parts, okay? 7 equal parts. 1 part, 2 parts, 3 parts, 4 parts, 5 parts, 6 parts, and 7 parts, equally spaced along the circle of radius 1. And you should note that the other 6 complex solutions are 3 conjugate pairs. Don't forget to label them properly, okay? And in my labeling for part C and part B, I'm sticking to the angles within minus pi to pi, the principal values, okay? Be consistent with the angle choices, but the question didn't say it has to be principal arguments. So you may want to write it like, for example, cease 8 pi over 7, cease 12 pi over 7, etc., etc. Okay. On the Argand diagram below, sketch the ray that originates. The ray originates. So the start point is always an open circle at the real root, which is z equals to 1. So I'll put an open circle here. And it goes through the complex number cis2 pi over 7. So this is cis2 pi over 7. So what I'm going to do here is label this one as W. And then starting from 1, 0, I will draw a, a ray like this. Okay. And that is the ray we should be drawing. Use ruler. And we want to find the equation of this ray in the form argument z minus z naught equals to theta. So the z naught should be the start point 1 plus 0I. Z naught is a complex number. Well, it's technically a real number, but a real number is also a subset of complex number, okay? And theta is measured in radians in terms of pi. So this is the theta we are looking at. We measure the theta from the positive x or real axis. Now, before we do that, we need to make use of this 2 pi over 7, but it's not equal to theta. Why is that? Because it's this angle, 2 pi over 7. Notice that this is an equilateral triangle. Let's say this is alpha. This is alpha. Sorry, not an equilateral triangle. It's an isosceles triangle. Isosceles triangle, let's say O, A, and a W, okay? So basically, we can say 2 alpha equals to pi minus 2 pi over 7 because the interior angle, sum of 3 interior angle will be pi for the triangle. And then 2 alpha equals to 5 pi over 7. Therefore, alpha equals to 5 pi over 14. But it's still not yet the angle theta because we want the supplementary angle of alpha. So theta equals to pi minus 5 pi over 14. That gives you 9 pi over 14, okay? All right, therefore, argument z minus 1. We don't need to write a minus 0i, okay? You don't need to write minus 0i equals to 9 pi over 14. So that is the equation of the ray described above. Okay, verify that the equation z to the power 7 minus 1 equals to 0 can be expressed in the form z minus 1 times z6, z5, z4, z3, z2, z plus 1 equals to 0. So left-hand side equals to z to the power of 7 plus z to the power 6 plus z to the power 5 plus z to the power 4 plus z to the power 3 plus z squared plus z. Basically, you just multiply z into each term and subtract a 1 multiplied by each term. So z to the power 6 plus z to the power 5 plus z to the power 4 plus z to the power 3, z to the power 2, z to the power 1 plus 1 equals to 0. And simplify your left-hand side, you will see they subtract each other. And eventually z to the power 7 minus 1 equals to 0. And that's verified. Because the question only provided you 4 lines, I don't think you should do, like z to the power 7 minus 1, then you divide it by z minus 1 and then repeat that process because you don't have enough space to write them down. So I would teach the long division process. But for some of you, you may want to use short division. Maybe short division. So like z to the power of 7 is actually z to the power 7 plus 0, z6 plus 0, z5 plus 0, z minus 1, something like that. So I will write it as 1, 0, 0, 0, 0, 0. Okay, hold on a second. How many zeros? 1, 2, 3, 4, 5, 6. 6. And you got a minus 1 here. And a factor is z minus 1. So a root is z equals to 1. So I'll put a 1 here. Now you drop down the 1 here. 1 multiply 1, that's 1. Add them up here. 1, 1. Multiply together, put it here. And Keep doing that, you will get 1, 1, 1, 1. If I'm not mistaken. And finally, should get a 1 here. Lastly, you get a 1 here, but once you add them up, you get a 0. So this is your remainder. So that indicates z to the power 6 plus z to the power 5 plus z to the power 4 plus z to the power 3 plus z to the power 2 plus z plus 1, okay? Is the other, I would say, hexic factor, okay? That means power 6, okay? Anyway, for 1 mark question, I think the most economical way is just expanding your left-hand side and cancel everything down nicely. All right, express cis 2 pi over 7 plus cis 12 pi over 7 in the form a cos b pi. A, b are positive real numbers. So cosine of 2 pi over 7 plus I sine 2 pi over 7 plus cosine of 12 pi over 7 plus I sine 12 pi over 7. Basically, if you observe what's happening with the two cosine terms, remember cosine theta equals to cosine negative theta, but it's also 2 pi minus theta, okay? And if you choose theta to be 2 pi over 7, then this bit will be 12 pi over 7. So basically, you just have two lots of cosine 2 pi over 7. And how about the sine term? Well, for sine term, we have sine minus theta equals to, let's say, sine 2 pi minus theta, okay? So what I'm doing here is do some match. You will get a plus I sine 2 pi subtracting sine 2 pi over 7, okay? Because this term will be negative sine 2 pi over 7. So they should cancel each other out, and you just get a real expression, 2 cosine 2 pi over 7, okay? For example, your A value is 2, your B value is 2 over 7 in front of pi. Okay, so lastly, given that W satisfies Z minus 1 times the hexic or degree 6 factor equals to 0. But this is not equal to 1, okay? This is definitely not equal to 1 because it's not the only real root. So use the given fact. We have W minus 1, W6 plus W5 plus W4 plus W3 plus W squared plus W plus 1 equals to 0. W not equal to 1. So W6 plus W5 plus W4 plus W3 plus W squared plus W plus 1 equals to 0. And W to the power 6 is a 6 12 pi. W to the power 5 is 6 10 pi over 7. And 6 8 pi over 7 plus 6, let's say 6 pi over 7 plus 6 4 pi over 7 plus 6 2 pi over 7 plus 1 equals to 0, okay? I think that's the intention of use the Moir's theorem. And previously, if we use the pattern here, in the previous part, we already simplified the sum of these two purple terms. Also, we can just do some, pair up. let's use blue here. And let's use, let's try to use another different color, orange here, okay? So the purple term will be 2 cosine 2 pi over 7 plus the blue terms. Well, choose the smaller angle. It will be 2 cosine of 4 pi over 7. And choose the orange term. You get a 2 cosine 6 pi over 7. Finally, don't forget the original equation has a plus 1 equals to 0, okay? We may want to make a note here. Note that we can pair 6 terms up using CIS, theta plus CIS, 2 pi minus theta equals to 2 cosine of theta, okay? So this is a general observation, true for any value of theta, okay? So therefore, you just divide everything by 2 and push that to the other side. You get a cosine of 2 pi over 7 plus cosine of 4 pi over 7 plus cosine of 6 pi over 7 equals to minus 1/2. And that's shown, okay? Okay, so that is in, I suppose that's the intention of the question itself. This is indeed a very nice and creative question. The 7th roots of unity and some nice trigonometric identities blended in it. Okay, I'll do one more question, and then I'll spend I'll find another time to do the rest questions like 4, 5, 6. So let's have a look at question 3. The curve given by y squared equals to x minus 1 from 2 to 5 is rotated about the x-axis to form a solid of revolution. Write down a definite integral in terms of x for the volume of the solid of revolution. So v equals to pi integral from 2 to 5 y squared dx. So we already have y squared. We don't need to reinvent the wheel. From 2 to 5 pi x minus 1 dx. Now find the volume of the solid of revolution. So basically, you can just type that in your CAS calculator, and I suppose you should get v equals to 15 pi over 2, something like that, okay? It doesn't specify any units, so I just write a units cubed here. And then you want to express the curved surface area of the solid in this form. Well, to make a better sense of that, when you chuck in 2 here, y squared will be 1. When you chuck in 5, y squared will be 4. So y will be from 1 to 2. So actually, we are describing some sort of solid of revolution. Like this, okay? And also we want to find the curved surface area. So we know y, the upper curve is y equals to square root of x minus 1. So dy dx is 1 over 2 square root of x minus 1. Surface area is 2 pi integral from 2 to 5. Remember now, this is y, okay? You need to multiply y inside the integral rather than outside the integral, okay? Because it's a function, not a constant. Square root of 1 plus dy dx squared dx. 2 pi from 2 to 5 root x minus 1 times 1 plus 1 over 4 lots of x minus 1. Notice that you actually square this thing, okay? To get a 1 over 4 x minus 1 without a square root. And then this is 2 pi integral from 2 to 5 square root of x minus 1 times 4x minus 1 on the top plus 1 divided by 4 lots of x minus 1 in the bracket dx. So then you will observe that square root of x minus 1 cancels with that x minus 1 in the square root. And you've got a square root of 4 here. And that should cancel out the 2 in the front. So eventually we are expecting just a pi here, integral 2 to 5, square root 4x minus 4 plus 1 minus 3 dx. So a bit algebra here, and we can just hence use this expression to find the curved surface area of the solid. Correct is 3 decimal places. You can see I hardly button pressed for this question. So I'm going to do shift plus 2 to 5 pi times square root of 4x takes 3 dx. That's the exact form, but I only want the answer to be 3 decimal places. So 30.84648, but we only focus on the 4 here, which is less than 5. So we just need 30.846. So for example, you can use the round button, round this answer correct to 3 decimal places, 30.846. All right. Just for the record, I'm writing down the full digits. 30.846 is that 4897 something. Okay. The total surface area of the solid consists of the curved surface area plus the areas of the 2 circular disks at each end. So basically, the diagram we sketched is very useful. So now, not only we are considering the curved surface area, but also we need to look at the 2 disks. The question introduced an idea of efficiency ratio or efficiency index something of a body is defined as its total surface area divided by the enclosed volume. So we want to find the efficiency ratio. Efficiency ratio is equal to the curved surface area. Let's just make some annotation here. So the green part, we actually calculated that from above. 30.846 or 8 ... plus the smaller circle has an area of 1 squared times pi plus a larger circle 2 squared times pi. The volume we get from previous part was at a 15 pi over 2. Yep. Okay, trust our CAS calculator. So you can type that into your CAS calculator. Make sure you carry all digits. So I get something like 1.975. 832 something. How many decimal places? Okay, 2 decimal places. Alrighty, so basically that's this 2 marks question. Another solid orbital revolution is formed by rotating the curve given by y squared equals to x minus 1 about the x-axis from 2 to k. The solid has a volume of 24 pi, and notice that this k must be greater than 2, okay? K must be greater than 2. So firstly, v equals to 24 pi equals to pi integral 2 to k x minus 1. Don't square it again. And we want to find this k. Let's see how we go. All right. This is a volume, remember? So we have k equals to 8. And next thing is we want to find the efficiency ratio for this solid, giving you answer corrected to decimal places. All right, so previously we used an integral like this from 2 to 5 to carry the calculation for the first surface area. Now with the new upper limit, we should be able to get another, curved surface area. And the new volume is your denominator, which is 24 pi. The new area, curved surface area, is this 75.916 something plus 2 ends. So the first end is 1 squared times pi. The second bit is like when you sub in 8 into square root of x minus 1, you get a square root of 7. So basically this is square root of 7 squared. That's the pi r squared bit for the larger disk on the right. And then you'll be able to get something like 1.34020, something like that, okay? So, well, let's go back and leave the last part. Check. Yeah. This is my final answer. Okay. All right. I will stop here for now, and I'll find another time to do the rest 3 questions and upload another separate video. Bye.